Hey, welcome to week 6. I'm Julian. I'm Mr. Krolak's pug, and I'm going to be standing in for him tonight. We're moving on, and we're going to take a look at Introduction to Linear Correlation. So if you've done work with scatter plots are when you when you draw a line, that's called linear correlation. Now, there's lots of different types of correlations. There's quadratic correlation, there's exponential correlation, there's logistic correlation. So first one we're going to look at is linear correlation, also known as finding the line of best fit. All right. Before we go any further, there's a big difference between correlation and cause and effect. Cause and effect sometimes being referred to as causation. All right, so correlation means mathematically that there's a relationship between two variables. And when we're studying data that has variables in pairs, that is known as bivariant data. So the bi indicating two data points. And it's typically one is an X and the other one's a Y. All right, so the correlation and causation. Correlation just means there's some sort of relationship. It doesn't mean one is necessarily causing the other to happen. And that's a very common error that happens is mistaking or misinterpreting causation or correlation to mean that one thing is causing another. And here's a good little TED talk that kind of spells out some really great examples of how correlation and causation can get confused. So let's take a look.
Welcome. I came here today to warn you about the dangers of ice cream. You may not be aware of this, but these innocent-looking cones full of sweetness are one of the major causes of drownings. And I've got the numbers to prove it. So if you plot a graph of the number of ice creams that are sold, and you compare it with the number of drownings, you can see there is clearly an upward trend. And I think it's very safe to conclude from this that we should ban ice cream, because it's very dangerous. Since you are all smart people, you've probably figured out there's something wrong with my example. What's really happening here is, of course, that there is an underlying factor, which is nice weather, you might have guessed it. And if the weather is nice, more people will go out swimming and unfortunately drown, and at the same time, more people will buy ice cream. And it's not the ice cream that's causing the drownings. And here it's really easy to see that there is something wrong, but jumping to an incorrect conclusion about causality when you see a correlation is the most often made logical mistake. And today my goal is to make sure that in the future you can recognize this mistake, and I really hope you can avoid making it in the future for yourselves. And I'll do this by just giving some famous examples. And the first one is really rather innocent. The fact is that married men live longer than single men. If you look at the statistics, you see that this is really happening. And women's magazines, they like to conclude from this that marriage is very healthy for men because it makes them live longer. Well, a friend of mine, he likes to joke that marriage mainly makes life seem longer, but that's because his wife is... But so, can anyone guess what's going on here? Because there is a causal relation, but it's the other way around. The fact is that men who are healthy and rich and well educated and have a much higher life expectancy, these are the men that are much more likely to find a wife. That's the way women are. And the guys who have a very low life expectancy, so they're unhealthy and poor, they are not as likely to get married. So it's the high life expectancy that is causing the marriage, not the other way around. Well, and this, of course, it's not so serious. No one will get married just because he read this. So let's move on to a more serious example. It was also more serious research. In Nature was a study in 1999 that showed that young kids who sleep with the lights on, that they have a much higher probability of becoming short-sighted later in life. Well, and the researchers, they were smart and they wrote very careful that they had found the correlation and they didn't know how the causal relation might work, but just to be sure they advised all parents to turn off the lights at night. And in the popular media, this became that bed lamps were night abuse, children's abuse, and that it was very bad if parents used lamps in the bedroom. And many parents were worried. I can imagine if this would have happened when my son was sleeping with the lights on, I would have felt really bad. But luckily, the article had to be corrected the next week. And maybe some of you can guess, if there are biologists in the audience, they know. Short-sightedness is genetic. And so it's parents who are short-sighted, and those are the parents who like to leave the light on in the bedroom. And they also are the parents who have short-sighted kids. So again, a simple mistake, easy to make. Then what is, I think, the worst example I know many of them. I see at least one of these in the newspapers every week. But this is a classic one. In the 70s, researchers found that there's a very strong link between kids who do well in school, get good grades, and kids who have a high self-esteem. And they concluded from this that it's very important to make sure that young kids are, raised to be confident and proud of themselves, because if their self-esteem is high, the good results will follow. And this was what was told to parents, especially in the US, for generations, that just make sure that your kid is proud and confident, then all will turn out well. And many years later, someone did another study just to see in which direction the cause was working, and they found that it was in the opposite direction. So the good grades were causing the self-esteem, and self-esteem wasn't causing good grades, and it was even worse. So kids who are raised just to have high self-confidence and not excel at anything, it can be sports or music, doesn't have to be school, but kids who are just proud of themselves and then fail at everything, in the end they will have a very low self-esteem and not be able to make anything of their life. So this was a very serious correlation mistake. And what I want for today is for you to remember that the next time someone wants to prove that there is a causal relation between something and something else, it can be anything. It can be vaccines and autism. It can be female bankers and the financial crisis. And if they point out to you that there is a very strong relation, remember that it's not enough to have a correlation. It gives a very good hint of what might be happening, but before you can conclude that one thing causes something else, you need to know why it does and how it does. So when in doubt, just remember the ice cream. Thank you very much.
Correlation between bivariate data. We're going to plot that data on a XY axis. The x-axis contains the independent variable, and the y-axis contains the dependent variable, and we plot the points just like we would plot points if we were in algebra class, an x-coordinate and a y-coordinate. So let's take a look at an example of how this works here. So recognizing a linear correlation. All right, we've got a group of students here, and we've measured from each student a horizontal jump and then a vertical jump. And our experiment is to see if there's any relationship between horizontal jump and vertical jump. So to investigate this, we're going to start by making a scatter plot. So to help speed things along, Desmos is a great tool for making scatter plots. So I'm going to pause a minute here, and I want you to open up a Desmos graph, and I'll show you how to type in this table and then what commands you use on Desmos in order to do a linear correlation or linear regression line. So see over at Desmos. Okay, I went to Desmos. I just opened up a blank graph and I gave it a title, horizontal versus vertical jumps. And for this experiment, we're going to use the horizontal to be the independent and the vertical to be the dependent. So we're going to see, is there a relationship between how far somebody can jump horizontally and how far they can jump vertically. All right. So we have to first type in this data. So to type in data in terms of a table, you're going to go up to this plus sign, and you're just going to choose table. Now you can call these variables anything that you want. You can type phrases in there, it doesn't matter. But you want to start with something that's like x1, x2, x3. And to do that, if I wanted it, let's say I had a different column and I wanted to make it an x2, I just type x2. All right, so we're just going to leave it as x1. And what I want you to do is go through and you just type in the value, hit enter, type in the next value, go through and do that, put your horizontal jumps in your in your X column, okay, and put your vertical jumps in your Y column. And I'll see you back in a couple of minutes. All right, we're back. Now I typed mine in, but I can't see anything, and that's because, remember, if you look at our X data here, it's all the way up in the hundreds. So I can either scroll out, like so, and now I can see my data. All right, you can also change by going up to the wrench up here on the right, and you can just change your scale. So for example, I could have set my X scale to go from 0 because we don't have anybody jumping a negative. That wouldn't make any sense. And the highest number is like 300. And I could say, all right, I want to count by 20s. You can set that up any way you want. Anytime you scroll, it's going to start changing. If you have like a little scroll thing on your mouse. Okay, so there is our data. And now we want to see if there's a correlation. All right, so you got these different types of correlations. Does it look like you could draw a line through this and somewhat fit the data the best that you could? All right, so it appears that there's like a moderate positive correlation. And the reason I say positive is that this line that I drew has a positive slope. And that means is the farther you can jump horizontally, as that distance increases, your vertical increases. If one goes up, the other goes up. Had I drawn the line going down the other direction, having a negative slope, okay, like this blue line, then that would have a negative correlation. As the X is getting larger, the Y is getting smaller. Okay, so that's just an idea in terms of correlations. Now, the closer these points are grouped to this line, then the stronger the correlation is. So the correlations I just described are shown right here. This would be an example of a negative correlation. As X gets larger, Y gets smaller. And that's a fairly strong correlation because these points are fairly close to this line. All right, if we look at the next one below, this would be an example of something where there's no correlation. There's really no recognizable pattern in this scatter plot. Okay, here's an example of a quadratic trend. If we join this, we could probably join this with a parabola. So there could be a quadratic relationship between those two sets of data, between the X and the Y. All right, next one down would be an example of an exponential relationship. it sort of looks linear, but you can see it starts to kind of curve up there. And if I was going to draw a line, or actually a curve here, this is probably an example of exponential growth, sort of like what we saw with when we were first looking at the coronavirus, and now hopefully the virus is going into logistic growth. So different types of trends depending on the data. Today we're just looking at linear trends. All right, so you can estimate the line of best fit by just eyeballing it. And then we can use your calculator or Desmos to calculate the line of best fit. So first of all, let's talk about what you need to do in order to just eyeball the line of best fit. All right, so if we go back to our graph here, when you draw a line of best fit, you want it to go through the mean point. So what that means is find the average of the x coordinates and find the average of the y coordinates. Now on Desmos, that's really simple because we can just type in a command and it'll do it for us. Okay, so to type in to get the mean, so instead of having to add all these up and divide by 15, the x's, I can just type in the command mean parentheses x1. And what that does is it takes all the data in x1 and it calculates the mean. So that's 180. All right, now I want to find the mean of the y coordinates. So I just go mean parentheses y1, and that's the mean of my y coordinates. So the point roughly 180, 140, I want my line of best fit that I'm just going to kind of eyeball here to go through that point. All right, so I'm going to plot that point. So I'm just going to do it like this, mean x1, comma, mean y1, and label it, and I'm going to say the mean point. So as I draw a line of best fit now, if I'm just eyeballing a line of best fit, I'm going to eyeball that line, but I want it to go through that mean point. Okay, now we could all draw different types of lines of best fit. I'm trying to get a line that goes through that mean point and kind of evenly divides the number of points that are above it and the number of points that are below it. So if we're just eyeballing it, you could see that we could come up with slightly different versions of what we believe is a good line of best fit, which happens when you're just doing it by kind of eyeballing it. All right, but we can also have the calculator do it or a Desmos do it. Okay, so to put in our formula for to calculate the line of best fit, the linear regression line, we're going to type in y1. So we go y and then just 1. Now you use what's called the tilde symbol. Okay, so a tilde, if you go to open up your keyboard from Desmos and you go right down here, I'm pointing at it, you see that little squiggle, that's your tilde. So in Desmos, that means regressed against. So we're going to go y1 regressed against m x1, because we're just putting in the equation x1 plus b, mx plus b, I mean. So then, whoops. Now, plus b, and then that fits it to our data. It gives us the slope, so we can see our slope over here. And it gives us our y-intercept. So here's your slope. Let's highlight that. Okay, slope right there. And then the y-intercept b is right next to it. So if we needed to write an equation for this, our equation would be y equals point. Let's say we were going to 3 significant figures, so this would be 256x minus 5.24, and that would be our line of best fit. Now, this value, we're going to talk about this later. This is the correlation coefficient. This tells us how well our data fits the line. The closer this is to either 1 or -1, the better the fit. If it's 1, it's obviously going to be a positive relationship, very good fit. If it was -1, it would show a negative correlation. But the closer that is to either positive or -1, the better your fit is. Okay, and that's how you get the line of best fit using linear regression. So to re-emphasize, when you are doing a line for, you're just eyeballing the line, that line needs to go through the mean point. And that mean point is the average of the x coordinates and the average of the y. Now we had Desmos calculate it for us. Here's a GeoGebra applet in your Cognity chapter where you can adjust the mean point. So the mean point when we calculated a few minutes ago was 180, roughly 180, and then 40, like close to 41. Okay. Now from there, I'm going to adjust this line so that it goes through as many points as I can and try to make the distance, that the number of points above is roughly the same as the number of points below, and then use that as my estimation for my line of best fit. Okay, so I'd be saying like maybe something like, oh, I don't know about there. Yeah, that's not too bad. Okay, and when we did it on Desmos, I think our equation was y equals 0.256, so the slope was pretty close, minus 5.24. So our slope and our y-intercept, which is pretty close to what we're getting on here. All right, but the big thing is using the mean point, the average of the x's, the average of the y, and have your line go through that point. All right, that's it for linear correlation, just an introduction to it. Tomorrow or next lesson, we'll get closer. We'll take a look more at the correlation coefficient. And I'll see you next time. So take care and Godspeed.